In this class we are going to learn about ensemble models, ensembling technique, and one of the special case of ensembling technique is random forest technique, and then we will also discuss about boosting. So the contents are introduction to ensemble learning, how do we build ensemble models, how ensemble model work, what is bagging, building models using bagging, a special case of bagging, random forest, what is a random forest algorithm, how do we build random forest models, boosting, what is the boosting algorithm, how do we build boosting models. That's what we are going to discuss in this class. To understand ensemble modeling technique, we need to understand a concept called wisdom of crowds. What is wisdom of crowds? Let's take an example to understand what exactly is wisdom of crowds. The problem statement is, what is the monthly expenses of a family in our city? So whichever city you are in, if you want to know, or if you want to estimate, if you want to predict the monthly expenses of every family on an average, what is the monthly expenses? So that is the problem statement. You can use any technique. You can use simple descriptive statistics, or you can use many variables that will finally predict what is the average monthly expenses. So there are two cases. There are two sets of people who are building this model to come up with the monthly expenses of a given family. There is one on one side, there is one eminent professor. He is one of the world's best predictive modeler, world's best data scientist. He is building a model on single model, and he came up with an estimate. Now there are 100 assistant professors who are independent, who don't know each other. Each of them have taken this challenge, and they also each of them built independent models by doing their own modeling techniques or by collecting their own data, different variables. Each one of them built several models. Each one of them built one model each. So there is one model, there is one professor, he built one model, and there are 100 assistant professors who don't know each other, who are independently building 100 models. So one single model, professor model, predicted on an average estimated expenses, monthly expenses is $6500. 6,500 is the estimation from the professor model, from his model 1. Whereas 100 assistant professors together, like all of them have built different models, all of them got different estimates, but when we take average of all those 100 predictions, so some of them predicted that as 8,000, some of them predicted that as $6,000, some of them predicted the income as $7,500. Now when we take average of all those 100 predictions, that comes to be $7,200. Now here is the question. Now there is one model which says $6,500 is the estimated income. The average of 100 models which says $7,200 is the estimated income. So intuitively, what do you think? All these 100 assistant professors, they might not be as good as Mr. Eminent Professor, but they are well in their own, like they are good data scientists on their own. So they have built fairly good models. So intuitively, it makes sense to choose the average of 100 predictions rather than relying on one model. So one should. So what exactly is wisdom of crowds? This is just the definition of wisdom of crowds. Basically, an easy way to understand wisdom of crowds is, instead of taking one best model, or instead of looking at one best thing, maybe it is better to look at not very best, like fairly good models. Look at as many as fairly good models and take the average. Maybe the average, the wisdom of crowds is better than building one good model. So One should not expend energy trying to identify the expert within a group, but instead rely on group's collective wisdom. Instead of choosing one expert, instead of relying on his expertise, better to choose group's collective wisdom. However, this is important. However, make sure that the opinion must be independent. These 100 assistant professors should not talk to each other, should not be depending on each other. Otherwise, they will not be building 100 different models. They might not be carrying information from 100 different angles. If they are dependent on each other, model 1 is same as 2 as 3, then it doesn't make sense. All these 100 professors have to be independent, independently building the models. However, make sure that the opinions must be independent and some kind of knowledge of truth must reside with the some group members. What exactly that sentence means? Some kind of knowledge, the truth must be reside with the group members, which means at least these professors should have knowledge. Assistant professors we are talking about, they should be, each one of them should be at least good in their own. You can't take any random guys and then start asking them to build a model. All of them are also data scientists as well. So instead of trying to build a great model, one of the best model, it's better to build some independent, moderate or fairly good models and then take their average as final prediction. That is nothing but the concept of wisdom of crowds. Now that we understand what is wisdom of crowds, ensemble learning is completely dependent or based on the concept of wisdom of crowds. What do we do in ensemble learning? We build multiple models and then use the average or use all the models as the final model instead of building one single model. So let's see what exactly is ensemble learning. Imagine a classifier problem. We want to classify just a binary classifier problem with two classes. We want to classify the data point as -1 or +1 at the end of building the algorithm. So imagine that we want to build the best possible decision tree. Let's say we built one model that is one of the best decision tree. So it has almost say 91% accuracy. So we are doing a classifier problem here and we built a decision tree that has 91% accuracy. Now let X be the new data point. So now we have taken a new data point. Now we will use this decision tree that will finally predict whether that particular new data point is falling in class 1 or +1 or class -1. So let us suppose this new data point, our decision tree predicts this to be +1. Our decision tree is predicting this new data point as +1. Is there a way we can do better than 91%? So here the decision tree accuracy is 91%. Is there a way we can do better than 91% using the same data? Let's try to build 3 more models on the same data set and see whether we can improve any performance or not. So we have 4 models now. The first one is decision tree that is already built. Now we have built 3 more models. So that is logistic regression, neural nets model, SVM model. So we have model 1 that is decision tree, 2, 3, 4 those are logistic regression, neural network and SVM, and each of them have different accuracy. Logistic regression has accuracy of 90%, which is like error of 10%. Neural nets has accuracy of 91%, error of 9%. Decision tree, anyway, we have seen accuracy 91% and error 9%. SVM accuracy 92%, error 8%. But honestly, there is not much of real improvement. Earlier our accuracy was 91%, error was 9%. Now SVM doing slightly better job, accuracy of 92%, error of 8%. This is not really improving. much over what we had earlier. But let's see. What exactly is ensemble learning? Now what about prediction of the new data point? So our new data point X was predicted as +1 by the decision tree model in the initial first attempt that we built with decision tree. The model is predicting that value as +1. When we substitute new data point X, that is classified, that particular X falls in the class +1. Whereas here, if we see what is logistic regression fitting, when we use the logistic regression model, that particular X, new data point X, is predicted as -1. The new data point X is predicted as -1 for neural nets model. The new data point X is predicted as -1 again by SVM model. Only decision tree is predicting it as +1. So the combined voting model seem to be having less error. Why? Because we, instead of choosing one model, that is decision tree, if we choose the voting model, what voting model means, if we choose all the 4 model output and whichever is the highest voted value, let's say 3 of them are predicting as -1, only 1 is predicting as +1, so we should consider this intuitively. We would believe that point as -1. So based on voting model, we choose the final prediction as -1. So instead of choosing one model, if we combine all those 4 models and take the voting, then finally the prediction might be actually accurate than the initial single model approach. This is the actual philosophy of ensemble modeling. So instead of building one model, we build several models and take their voting. So instead of building one decision tree, we built 1, 2, 3, 4 models, and then each one of the models might not be very strong in their own, but we want to combine four of them and then take voting or average, then finally choose identify the predictor based on the average or the combination of all 4 models. This is the actual philosophy of ensemble learning. Now let us see what ensemble models in detail. So obtaining a better prediction using multiple models on the same data set instead of building one best model is nothing but ensemble technique. Not every time it is possible to find a single best fit model for our data. Ensemble model combines multiple models. Ensemble technique combines multiple models to come up with one consolidated model. Ensemble models work on principles that models that are moderately fairly good models, multiple such models give together high accuracy rate when they are combined together to make a consolidated model. All of them together make a highly accurate model for predictions. Understandably, building and evaluating ensemble models is quite computationally expensive. In the sense, instead of building one models, we are building multiple models. So the effort to build ensemble models is not same as effort in building one single model. Build one really good model is the usual statistical approach. Build many models and average the results is the philosophy of ensemble learning. That is nothing but the wisdom of crowds. So instead of building one best model, let's build multiple models and combine them for prediction. Why ensemble technique works? Let us see why really ensembling technique works. Why we get better results using ensemble model than building one particular model. So let us suppose we have 3 models, M1, M2, M3. M1 has an error rate of 10%, model M2 has an error rate of 10%, M3 has an error rate of 10%. So all these 3 models are equivalent. almost. There are three independent models using three different techniques or three different uh, types of information we have built the model on the data. Now three models have to be independent, so we imagine that they are independent. We can't build the same model three times and expect the ensemble model to reduce. So for ensemble modelings or for the wisdom of crowds, the basic requirement is all these models need to be independent. M1, M2, M3, they should not be doing the same thing. I mean, if you are building the same model thrice, then it hardly reduces any error. So M1, M2, M3, three independent models we built. Okay. In this scenario, the worst ensemble model, I mean, if we just combine these three models, the worst ensemble model will have error rate of 10% because each model has an error rate of 10%. That is the worst that we can do. What will be the best error rate of ensemble model? That means what will be the best ensemble model doing? So if we just combine these models and take the voting criteria, then we can simply derive the final error rate, that is 2 out of these 3 models predicting wrong plus all the models predicting wrong. Those are the only 2 scenarios where this ensemble model would go wrong. Remaining every time ensemble model will do better job than individual models. So let's not go into a lot of these details, but it can be derived that the best ensemble model will have, the combined model will have an error rate of 2.8%. It can be derived from using probability that the best ensemble model which combines these three independent models will have an error rate of 2.8%. So we just took three moderately good models, that is each one of them having an error rate of 10%, 10%, 10%. Just by combining them, but not doing anything else, just by combining them we can get up to an error rate of 2.8%. So the best ensemble model will have an error rate of 2.8%. So what are the types of ensemble models? So the example that we have seen is a very primitive type of ensemble model, that is just to give you an idea of this whole ensemble technique. That is not how ensemble models are built. There are specific cases, specific techniques. There are better statistically stronger ensemble methods that will yield better results. So we will see a statistical or more scientific way of building the ensemble models. Two of the most popular ensemble methodologies are bagging and boosting. But by now you should understand the overall concept of ensemble technique. Instead of building one model, we are building multiple models and taking their voting. So that will reduce error. If you take the voting, very rarely you will prone to get errors. At least you will have accuracy more than what each of these individual models has. So there are two most popular ensemble methodologies that are, one is bagging, the other one is boosting. So we will understand the techniques of bagging and boosting in coming sessions.